Hi everyone, so today we're going to be doing electricity past paper questions from 2017 to 2021, and hopefully you'll pick up on some key things you would need to apply to your, well, key techniques that you would need to apply to answering your questions during the exam, which is tomorrow. Okay? All right, so here is this question. Sometimes you get questions based on the battery or the cell, because a battery is a lot of cells put together. Okay, so here we have a battery. Well, here we have a cell, okay? And we must remember that a cell is one, and many cells will be referred to as a battery, right? So a cell is a power source. It's a portable power source, right? And many cells will be referred to as battery. But we use that incorrectly all the time. But just be aware of it when you're doing the exam. Okay. Now they ask us to label the cell. So the centerpiece is called the carbon rod, and then we have the we have the ammonium chloride paste. Again, we have the carbon rod, okay, that's the positive terminal, and then we have the ammonium chloride paste, okay. All right, then the next part asks, it says the zinc carbon cell is a primary cell, while the lead acid cell is a secondary cell. So it says state three differences between these cells. Well, I went all out because I want you to get it in case to ask this question. So first of all, a zinc carbon cell is one-time use, while the lead acid cell is rechargeable. The zinc carbon cell is relatively cheap. Lead acid cell is expensive. The zinc carbon cell has a short time span, while the lead acid cell has a long time span. The zinc carbon cell takes up very little space, whereas the lead acid cell takes up a lot of space. But not a lot, but in comparison. The voltage that's supplied by the zinc carbon cell is 1.5, and the lead acid cell is 2.0 volts. You get about 1 amp from a zinc carbon cell and more than 400 amps from a lead acid cell. The reactive paste, what drives the reaction forward is ammonium chloride in the zinc carbon cell, and in the lead acid cell is dilute sulfuric acid. Now let's remember that the zinc carbon cell is small and light, while the lead acid cell is large and heavy. Now they came on here with a calculation. It says a solar module power source is used to charge a 12-volt battery. During one phase of charging, a constant current of 1 amp is supplied for 4 hours. Calculate the charge added to the battery in coulombs. So what I always tell students to do, and what I do to make my work easier, is I list out all the variables that they would have given me. They gave us the voltage, the current, and the time. Right? So we have 12 volts, 1 amp, 4 hours. But remember, we need to use SI units when we're dealing with these formulas. Whenever we're trying to solve something, we usually use SI units, as in standard units. So we have the standard unit for volt and current, but we're not supposed to be using hours for time. We're supposed to convert hours to seconds. So I have the little conversion over here where I have, if 1 hour is equal to 60 minutes, then 4 hours will be equal to x, and that's 1 over 4 equal to 60 over x. Transpose, we get 4 times 60, that's 240 minutes. Then we have to convert the minutes to seconds. So if 1 minute is equal to 60 seconds, then 240 minutes will be equal to x. 1 over 240 equal to 60 over x. Therefore, 240 times 60 over 1 is equal to 14,400 seconds. Take this time, multiply it by current, because to solve for charge in units of coulombs, you say Q is equal to IT, or kit. And so I represents current, T represents time in seconds. Multiply that, we get 14,400 coulombs. Then they asked to calculate the energy in kilojoules added to the battery. So energy is related to voltage and charge in this format. So voltage is equal to energy divided by the charge. Okay, so if you want to solve for energy, you transpose and make E the subject of the formula by multiplying both sides by charge. And you get E is equal to, our energy is equal to voltage times charge. Using the charge that we calculated or determined above, we multiply it by the voltage that we were given, which was 12, and we end up with 172,800 joules. Written in kilojoules, that's what they asked for, is 172.8. Now, to convert from joules to kilojoules, all you do, students, is divide by 1,000. And that's 4 marks. 4 marks. Alright, so now we have suggest with a reason a value for the voltage of the solar module during battery charging. So the value for the voltage of the solar module has to be greater than the voltage of the battery for it to charge, because to push charges into anything there needs to be a voltage difference. So a value for the voltage of the solar module may be anything greater than 12 volts, for example, maybe 15 volts, may be appropriate, or even more. So just know to get to charge up something, whatever is doing the charging must have more driving force to push the energy into the system than what they're charging. So that's my rationale for that. 15 points was for this question. Okay, so now this is how they might bring another electricity question, and sometimes they only focus on gates, right? Logic gates. So you could either do a question that deals with, they like to bring, these are the major ones. They like to bring the battery question, they like to bring the logic gates question, they like to bring transformer questions. Sometimes it's a mixture of both, and their least liked one is often the DC motor or the generator questions, right? So I put a little bit of both, of all, sorry, I put a little bit of all here. So here we go. State the name of each logic gate represented below. Okay, so you should know your logic gates, and if you don't, here goes. So a NOT gate, that's the easiest one. It's a triangle with a circle attached to the pointy part of it, right here. I mean, they have 3 points, but you know which one I mean. The major pointy part. We call that the NOT gate. And then we have the AND gate, which is a round head. And then we have what is the OR gate attached to a NOT gate to give you NOR gate. So not an OR gate. So without the round nipple here, this would be an OR gate, but this round nipple is an indication that you have a NOT gate attached to the OR gate to make it a NOR gate. That's really what it is, right? I have a video on this, so maybe I could put the link for the video below, so check for it. If I don't do it, check for it in my videos. It's there. There's a whole description, a whole video describing explaining the logic gates. Okay, so it says complete the truth tables for the NOT and NOR gates. So this is either you know it or don't. And again, I have the video where you don't even have to memorize these things. They're very easy to remember once you understand what you're doing. So with NOT gates, we call them converter gates. So if you have an input of 0, it will be converted to 1. And if you have an input of 1, it will convert to 0. So if you have 0, it's 1 for output. If you have 1, it's 0 for output. So, you know, it's just a converter. That's why we refer to the NOT gate as a converter. So with the NOR gate, which is not an OR gate, we say the OR gate is like an addition gate, right? So with addition, usually we say, well, 0 plus 0 gives you 0. So if this is not an OR gate, it will give you the opposite of 0, which is 1. 0 plus 1 should give you 1. So if it's not an OR gate, we're going to give you 0. And the same thing goes here, because this is the same as up here, just reverse. So this will give you 0 as well. And 1 plus 1, we will say going to give you back 1. Because we don't get any higher than 1 in binary. So 1 plus 1, 1. And so, seeing as how this is not an OR gate, as we could say, seeing as how it's attached to a NOT gate, the NOT gate will convert whatever should come out. So in an OR gate, this should be 1 plus 1, 1, give you 1. And the NOT gate will convert this 0 to a 1. That's really what is happening, right? So these will be your outputs here. So again, visit that video because the video will help you to understand logic gates, okay? Okay, so following on now, it says Figure 5 shows a basic home security system that provides protection for 2 windows and front and back doors. The use of OR gates facilitates the system with all inputs on low, which is 0. So if a disturbance occurs, the input turns to high, which is 1. Now the alarm will only sound if a high output is received. So we could see it here when the windows are closed and the doors are locked. We have an input of 0. 0 plus 0 gives 0. So the output is 0. 0 plus 0 gives 0. But these are all OR gates. And so the alarm is off. No. It says here, Figure 6 shows an intruder, a big thief, at window 2. It causing its output to change to high 1, right? So the question now was to find the logic combination that causes the alarm to sound by determining the outputs at A, B, and C. Again, if you understand logic gates, this was like a giveaway question. This was so good in terms of 0 plus 1 for OR gate will give you 1, and 0 plus 0 will give you 0. So these are the outputs at A and B. A and B will be 1 and 0. So we put the 1 and 0 here. Now please put the answers on the lines provided. Don't go and make any space for your own little answer. They're not going to correct it. Put it on the lines that they provide. You know, you could always write here to tell yourself, okay, I have the answer. You can write in pencil and then in pen you write it here. And then now for A and B, this is another input. The outputs now become inputs for this particular gate, this OR gate right here. So 1 plus 0 will give you 1. And definitely we are correct because remember the alarm only comes on high, which is 1. So 101 would be our output. To make matters worse, if you didn't know logic gates, they come with a second question. Oh my God. And they say, if a simultaneous disturbance is triggered at the back window, so now you got 2 robbers, one coming through the window, one coming through the door, right? What will be the logic output? No, they give us the inputs here, what happening. So whenever you open these things, they turn to 1. So remember again with OR gates, we said that they're addition gates. So we add these two. We said 0 plus 1, you get a 1. 0 plus 1, 1. And definitely the alarm need to go off because 1 plus 1, something from something will give you something. You're going to get 1 here. So the alarm goes off and they put dashes. So your answer is supposed to be right on these lines. Okay, unlike this, they could have put dashes here, but no. Let's put our dashes over here. Anyway, so moving on, they said state 3 ways in which advances in electronics, such as the introduction of logic gates, have made a positive impact on society. Now, your textbook has a lot. I wrote my own. Your textbook, I remember kind of the textbook too. So here we go. Improved communication, of course. We have increased storage of data. And we have data which is easier to access. You know, like now your textbooks could be made into PDFs. Now tests could be made into PDFs one time. So you don't even have to worry about paper usage that take up a lot of space. Like you should see my room right now. I wish everything was like the way it is now. Yeah, so yeah, that would be the answer. But you could always find the answers in the textbook. I forgot which page, but there's a PDF format for the Collins concise text, and the answers are right in their children. They're right in their students. I should say students because some of you might just be private students as well. All right, so here we have another one. They like to bring this one too. I think electronics or electricity is often the weakest section. It's often a section that causes a lot of problems to students. I understand, because there's a lot to learn. There's a lot to really process. Okay, for number 6, it says figure 6 shows a magnetic field when the poles between the poles of a strong magnet. So what we need to realize here is that the direction of the magnetic field lines always go from north to south. Always. So make sure you make note of that. The direction of the arrows always go from north to south. Okay? And it says, complete the following diagram to show the magnetic field due to a current carrying conductor where the current is directed into the plane of the paper. So what I want y'all to do is to give a thumbs up on your right hand. Give a thumbs up on your right hand right now, okay? And look at it. And take that thumb and push it into the computer that you're looking at right now where the X is. Push it in. Now what I want you to do is to realize where your fingernails are. Your fingernails are in the direction of the arrows on my circles, right? So your fingers actually tell you the direction of the magnetic field lines that are existing around the current carrying wire. Okay? So your thumb is the direction of the current. So because the current, the X in a circle represents current going into, your thumb should be going into the computer right now, and your fingernails should be going into your palms in a clockwise direction. Right? So that is how you figure that one out. Okay, so that's called the right hand grip rule. Okay, now the resulting magnetic field when the current carrying conductor in A1 is placed between the poles of the magnet. So the current carrying conductor, the conductor basically that is carrying a current through it, is going to disrupt the magnetic field lines, and the magnetic field lines are going to push down the wire. Okay, they're going to push down the wire. And this is where you would incorporate what do you call it? You would incorporate Fleming's left-hand rule. Okay, and we're gonna dive right into that in a while. But in Fleming's left-hand rule, what you would do is you put your, I can't even describe it right now. So I'm gonna show you on the next page. But you need to have a bunch of fingers involved, and the FBI and all of that gonna be in there, right? So yeah, just the FBI, not the CIA or the DEA, but the FBI. That's who you're gonna be dealing with, you know. All right, but just note that whenever you have a current going into the paper or into the screen, that the magnetic field lines will cause the wire to move down, and if the current was coming towards you, which would have been a dot, like you see a dot here, then with that one, the current was coming towards you, guess what? The wire would move up. And I feel like they will bring a question like this just to upset you. You're not coming towards. Because in the book, this is exactly what it has there. This is an exact example. And what I find with CXC, they tend to like switch it up. They flip the switch on you, and to see if you understand what you're doing and you're not just, you know, sucking in information without reasoning. So just note that if you have a current carrying wire out of the paper, so if this were a dot and not an X, the wire will be pushed up. Okay, these field lines will cause the wire to move upwards. Okay, so yeah, so on this page I put a picture so you can see the FBI, right? So each of these fingers are at right angles to each of them. So this is at right angles here, and this is at right angles here. And what we're dealing with is a DC motor. So whenever you deal with a DC motor, right, and they ask you how is the coil going to move, which side gonna move up and which side gonna move down, always remember that you're gonna be using Fleming's left-hand rule. And how I remember that for the motor is that LM in the alphabet, M comes right after L. So LM, so left hand rule for motor, because the right hand rule is used for generators, right? So there's a left hand rule, Fleming's left hand, and there's a Fleming's right hand. The left hand rule is used for motors. Just remember that LM, LMNOP. You learn the ABCs for a reason. So here's what we have. We have the force on the thumb, the direction of the magnetic field on the second finger, and the current on the third finger. Well, they call the index finger the first finger because they don't recognize the thumb as a finger. The outer odd and outer place, eh? But just note that the index finger is the magnetic field, and it always goes in the direction of north to south. Okay, so that's why I have it like this. So this finger is going from north to south, and then the current now is coming towards you. Now here's another special tip you need to note. Whenever you're dealing with these types of setups in physics, you need to, unless otherwise stated, you need to just refer to the conventional flow of electrons. But that's a story coming up for you in a bit. Hold on. So the first question says, name the path labeled X. So the path labeled X is called a commutator or a split ring. Split right here. So you could put split ring or commutator. Either one is correct, right? That was 1 mark. Now, when we speak about the conventional flow of electrons, that's where we speak about the movement of positive charges if they could move, right? And that was something based on history by Benjamin Franklin, who got it wrong, but because all of the formulas and everything in physics is based on how he thought electricity moved, they just kept it as is, because they found that they would have gotten into a lot of problems, having to switch things around and all sorts of things. Imagine one wrong thing, one mistake caused this whole world to just work through it. Let's just ignore the mistake. Let's ignore it, right? So that's why I always tell people, make sure you get it right the first time. All right, so because of that, we consider the movement of positive charge coming from the positive terminal of the battery. And I know some of you probably have problems with this, eh? So conventional flow of electrons, we consider the movement of positive particles if they were able to move from the positive terminal of the battery through this circuit. So we're going from the end here through this circuit and around into the negative end. Okay, that is how we see conventional flow of electricity. The real thing, the one that really happens, that we acknowledge but we don't use in our calculations because it can cause a lot of problems, is electron flow. In actuality, electrons actually come from the negative end, because those are the particles that's actually moving. The particles that actually could move are the electrons. And again, when you go up higher into physics, you realize that electrons are not the only things that can carry a charge and that can, create a flow of electricity. You have ions, that can do that when you're dealing with electrolysis. But that's me babbling again. But anyway, so we always consider conventional flow of electrons unless otherwise stated. Now here goes. It says, explain what happens when the switch is closed. And this was a cop out for CXC. This is such a hard topic, a topic that is hardly ever grasped well by students, and they're going to make it a big thing. 9 marks. They probably run out of questions. They ran out of questions there. Anyway, so it says, explain what happens when the switch is closed. And you're just thinking like, what, and why? And it says, your answer should include the direction of the current, the forces acting, any rules applied, and the direction of the rotation and how continuous rotation is achieved. My lord, so just hurt the students more. Anyway, so first thing we need to understand is that when you come to motors, you always know the direction of the current based on how the batteries turn. So if you have the positive end, just remember you're going to start your arrows from there and go through the circuit one time, right? So wherever the positive end is, start going away from that positive terminal through the circuits. And then you just continue along your merry way through the coil. So you always know the direction of the current, and you already know the direction of the magnetic field. So the only thing you need to solve when it comes to DC motors is the movement, which side will move up and which side will move down. So I always tell students, make sure you pick a side. So I always tend to move to the this side. For some reason, I'm strange. And luckily enough, which is what I must be happy about, and I am happy about, is that they went from north to south. They went from north to south, going from left to right. Because when you start to go from right to left, your hands tend to not do what they're supposed to do. Because, I mean, it's your left hand you're using. You want me to twist it all over the place. But anyway, no. I want you to put up your physics gang signs, okay? Like this picture. Fix up your fingers, such as that you have the F, B, I. FBI, F for force, B for magnetic field, and the I for the current. And choose a side. So I'm choosing side AB, right? Now look at the current. The current is coming towards you from side AB. So the current is your middle finger. Take your middle finger and put it to your chest. Put it to your chest, okay? And then take your index finger and look at it. Line it up now with north to south. So that means from the joint on the palm of your hand to the tip of your finger should be going from left to right, okay? And then look at your thumb. Where is your thumb facing? Up in your mother roof. Oh yes. So AB will be going up in the ear, right? So if AB is going up in the ear, then DC will be going down. So it'll be going in the opposite direction. And so because of that, the coil will be moving in a clockwise direction. So that is one problem solved, okay? So this is how I wrote up mine. I wrote it up in a nice way. And the actual answer is in the green section. And then I have an important notice for you, which is what I babbled about just a while ago. And I'm going to read it because, hello, I spent time making sure it was written well, okay? So gem time, let's go. Fleming's left-hand rule is used to determine the direction in which the coil would turn, okay? Now, according to the conventional flow of electrons, electricity flows from the positive end of the cell's terminal through the circuit to the negative end of the cell's terminal. Now, knowing the direction of both the flow of the current and the magnetic field lines, which runs from the north pole to the south pole, applying Fleming's left-hand rule, side AB of the coil will move up, while side CD will move down. Hence, the coil will move in a clockwise rotation. Now, I answered all of them. I answered the direction of the current, the forces acting, any rules applied, I answered all of that. And notice the direction of the rotation, I answered that, right? So that was 3 paragraphs. Now, the final one was how continuous rotation is achieved. Here goes. The split ring is fixed to the axles and allows the coil to rotate by switching connection between the coil and battery every half revolution. As it rotates and rubs against the fixed graphite brushes or contacts. Pull stop, boyaka 9 max. Watch here. So easy, right? I hope you all understand. No. Understanding, with understanding comes, you reap the rewards because you're no longer fighting to write things verbatim. You understand what's going on. So this is why this happens. So listen. It is important to note that conventional current was established during the discovery of electricity. Conventional current is the direction in which positive charge would flow if they were free to do so. It is the direction of the electric field. However, this discovery was wrong since electron flow is what actually happens in a circuit. Electron flow is when electrons flow from the negative terminal of the cell through the circuit and into the positive terminal of the cell. Hence, electron flow is the movement of flow of electricity in the opposite direction to that of the conventional current. So you see how this is going this way? In electron flow, it will be going this way, from this terminal this way, right? Now, it must be noted that the direction in which current flows does not affect what the current does as long as it flows consistently, okay? Now, however, this is where the however come in. However, the conventional flow current is still used in calculating and solving problems because the rules change. Changing from conventional current to electron flow will cause a lot of confusion while reasoning or performing calculation. If the rules change, the right-hand rules in conventional current will become left-hand rules when applying electron flow, since the direction of the current would change. So again, if you were to put the direction of the current going this way, you would have to use Fleming's right-hand rule, right? You would have to use Fleming's right-hand rule, which is basically the same setup with your fingers there. And because I'm using my right hand, I would use side CD. And again, now I would have to turn my hand, my finger, turn it away from you, turn it away. So instead of you going, normally you would set up your hand like turn out your hand, open out your hand away from your chest if you're going to shoot somebody, and put it to the side of your body. So like it's not in front of you, but to the side, right? And now you have your north and south pole, right? That's your direction of your field lines. And then you would see that the current, where is the current going? So you got the north and south. Right, so now what would happen is that inside CD, the current now will be coming towards you. Because remember, the direction of the current would change, right? So it won't be going away from you, it will come in towards you. So now rotate your whole hand back, like you're turning your hand around, and you're going to realize that with the Fleming's right hand rule, that this side will go down. So you see, you would have to change up everything. You would have to change up everything, right? All right, so you probably were like, what? Just remember, put your fingers on your right hand. If you were doing the electron flow on your right hand, set them up just like how the picture is there, right? So you have your 3 fingers at right angles, and just open out your hands as if you were on a floor, and you open out your hands wide, like Jesus on the cross, but just one hand. So you're like Jesus on the cross, but one hand, right? And then with your hands open out wide now, you would rotate that hand around. So just imagine you would like the world, like you're turning your hand right around where your thumb now is facing to the ground, because your middle finger is the direction of the current. Because remember, the direction of the current would switch with the electron flow, and you can see now that the thumb is facing down. So if you had to use the electron flow, you would have to use your right hand, Fleming's right hand rule, and you see where the confusion sets in. So that's why they just kept it as is. Listen, we done build all these laws based on this wrong information. So seeing as how it doesn't hurt anybody, because if we were to do that, then we would have to change up all the laws again and everything and confuse everybody. Let's just keep going with it, because we're getting the same answer anyway. That's what happened, it was serendipitous. They ended up getting the same answers, and they were lucky, and they were just like, listen, we're going to just call this conventional current, and we're going to just tell everybody that the real thing is electron flow. Don't worry about it, just apply the rules, and you're going to get the same answer. That's what it was. Okay, so now we're moving on to the next question. It says, house wiring circuits contain fuses and earth wires. Appliances are connected to these circuits in parallel. What is the purpose of the fuse in a circuit? It melts and breaks a circuit when a current that is too high flows through it to prevent damage to the device, right? So that's the use of the fuse. All right, then it says, what is the purpose of the earth wire in a circuit? Well, the earth wire is placed into a circuit to avoid electric shock or electrocution of a person when an appliance experiences a short circuit. The earth wire also prevents the live wire from overloading and absorbs the excess or leaking electrons from the electrical appliance to the ground. A person can become shocked or electrocuted when a live wire becomes loose, and if there is no earth wire to redirect the flow of electricity to the earth. The next person who uses the appliance will become the earth wire and suffer from a severe shock, or worse, an electrocution. It says here, state 2 reasons why appliances are connected to the circuit in parallel. Well, 1, appliances can be switched off and on without affecting each other once you have a parallel setup. And 2, appliances can be designed to operate on a single voltage. So those are 2 reasons why appliances are connected in a parallel circuit. Okay? Remember, remember with series circuit, one appliance mash up in a series circuit what's going to happen is that all the appliances will stop working because there's only one way for the there's only one path for the electrons to travel or electricity to travel. So it's like that appliance not working is breaking the circuit. All right. Says here, use the circuit diagram in figure 5 to determine the total resistance of the circuit. Alright, so this one is nice. So you have to recognize that sometimes resistors could be placed in series and sometimes they could be placed in parallel. And they're treated differently. If they're placed in parallel, their total resistance is calculated in a different way. In this case, we have two resistors in parallel, and we could use something called the product over the sum, right? We could use that, which is a quicker way to solve for total resistance in this arrangement than to do the 1 over Rp equal to 1 over 6. And you know what? I would often encourage students to use this way, the sum over the product way, when you're dealing with two resistors, so you could get your answer really fast. But just know if you have three resistors, you cannot use the product over sum. Not with three. Well, it depends on how it is done in three, actually. So I can't answer that, because there's some ways that you could use it in three. If you have a series running down here, you could actually use it. But anyway, I would just say if you have them singly like this is what you would use. If you have 5, you would use the setup 1 over Rp equal to 1 over 6 plus 1 over 4. And this is the symbol for ohm, by the way. That's how I write it. It's funny. It's like a man walking forward, half a body of a man. But anyway, if you look at it, I use it two different ways and I got the same answer twice, which means I'm good to go. And once I calculated this area, I simply added it to the sum of these two, because these two are in series. So I would add 2 plus 3, get 5 ohms. So 5 plus 2.4 will give me 7.4 ohms. That's the total resistance overall after I finish doing my paths, parallel and the series section. Now the actual total current in the circuit. So we have to remember how voltage and resistance are related. They're related such that voltage is equal to the product of current times resistance. So to make I the subject of the formula, you divide voltage by resistance, and we get 3.24 amps. The final question for this particular question was, which fuse, a 2 amp fuse, a 3 amp fuse, or a 4 amp fuse is the most suitable to use in the circuit shown in figure 5? Well, it would be a 4 amp fuse. If you use a 3 amp fuse, no current will be able to flow through the system before you could even use it. It will blow. So you have to use a fuse that's a little bit above how much current is allowed to the system. It's a little bit above. Not too much above, otherwise the system is going to overload and destroy the devices attached. Okay, so here is another question. Now it says draw the electric fields of each of the following arrangements. So again, based on the old days, how the site was that the positive charges were moving, so you have to pay special attention to the arrows, the direction of the arrows. So with a negative charge, you would have arrows going towards the negative ion, and with positive charges, with negative charge, and positive charges, they're going away from. And then we have a positively charged bar with a negatively charged particle, and we have it, being attracted to. So this will be the drawing right here. Then it says, now we have a calculation. It says, if the number of electrons transferred from a charged rod to earth through a wire is 4 times 10 to the 8, and the total charge transfer is 0.64 coulombs, calculate the size of the charge in 1 electron, or on 1 electron. Well, sometimes I do these things called ratios because that's how I understand it. And I would say, well, if we have 4 times 10 to the 8 particles, right, are electrons. This is the amount of electrons, and the total charge of this amount of electrons is 0.64, then we could figure out how much the charge would be on one electron just by a simple ratio. And it turns out to be 1.6 times 10 to the 9 coulombs, because this is actually 4 times 10 to the 8 over 1 equal to 0.64 over x. And I would just transpose and solve for x. And guess what? There's an equation for it. You could use charge equal to number of particles, change the charge on each particle. And once you solve for q, the small q, the charge would be in 0.64, as you can see here. And the number of particles would have been underneath, and you get the same answer. So my reasoning was correct. So sometimes your reasoning sometimes you do not need an equation. Sometimes, not all the times, right? Now then they said the current that flows through the wire, if it takes 0.4 seconds for all the electrons to flow to Earth. So again, we just incorporate Q equals to IT. This is another relationship with current and time and charge. So charge is equal to the amount of current times the time that it takes for that current to do whatever it's doing. And so they said to solve for the current. So current is equal to the charge over the time. So we have already calculated the charge, right? And I will never do something wrong. Hope I didn't do something wrong. Takes the current that flows through the wire, if it takes 0.4 seconds for all the electrons to flow to Earth. Ooh, so I think I have a little mistake here, because this is the charge of one electron. So I have to multiply it by 4 times 10 to the 8. Yeah. This is the charge. This is the number. This is the charge of 4 times 10 to the 8. So it says the current that flows through the wire, if it takes 0.4 seconds for all the electrons to flow to Earth. So since this is, so I need to use 0.64 over 4. Let me fix that. Let me get my eraser. Let me fix this. And so this would be, so if R for all the electrons, so because it's all 0.64 divided by 0.4, and that will give 1.6 amps. 1.6 amps. My bad. Let's hope this is, because I'm looking at this as this is my interpretation. The current that flows through the wire, if it takes 0.4 seconds for all the electrons to flow, so all the electrons had a charge of 0.64 coulombs, and this is the time to be 1.6 amps. Okay. Well, I mean, if you don't see it this way, just let me know. But this is how I see it. My reasoning shouldn't be that off. So the answer will be 1.6 amps, right? Now it says state the direction in which the charges will flow if the rod is positively charged. Well, electrons are the ones that move, right? So based on electron flow, they should move into the Earth. So I would say based on electron flow, I should actually state it as which says based on electron flow, they should move into the Earth. And that's what I would do to cover my backside. I would say based on electron flow that would travel into the earth. But based on, let me see, this is the number of electrons transferred from the charged rod to earth through a wire. But based on electron flow, I would say that they would move into earth. They would do the opposite, they would go the opposite direction if it was conventional current, if we're looking at it that way. But I'm going to base mine on electron flow. Now it says, state how the static buildup of charges on a vehicle could be hazardous. Well, a static buildup of charge on a vehicle could cause sparks. Now, if this vehicle is at the gas station, it could cause an explosion to happen if gas is being pumped into the vehicle. And how can this happen? The spark can jump from the car to the metal nozzle of the gas pump, producing a flash fire through the flammable vapor. So you could actually die if you don't discharge, right? Okay. Here goes now. So this is another one. This is another DC motor question. But guess what? It's a little simpler than the other one. I actually like this question, you know. It says figure 6 shows a simple DC motor which consists of a coil of wire A, B, C, D between the poles of a magnet. The dotted line represents an axle about which the coil can turn. A current flows through the coil in the direction shown by the arrows, right? And look at what they did. This is what I absolutely dislike. Let me see if I could find. I wonder if this has laser pointer, because I need it to. So basically, this is what I don't like, when they have the north over here and the south over here. They try to catch you every time, right? So this is what I'm gonna say. Just remember, the direction of the magnetic fields always go from north to south. Always. Draw the magnetic fields between the poles of the magnet in figure 6. Just do not forget that the direction always goes from north to south. Okay, so make sure you have your arrows going from north to south. Then it says state the direction in which, say, dA of the coil will move as the current starts flowing through the circuit. Let's not forget Fleming's left-hand rule is used for DC motors. Remember LM, LMNOP, LMNOP, LMNOP. So L, left-hand rule, Fleming's left-hand rule, and they already gave us the direction of the current, which was nice. But they wanted us to find out the direction of the magnetic field. So using your left hand, okay, you take your second finger, well, you open out your hand, do the Jesus thing again, open out your hand like Jesus, but this time on your left hand, and your second finger, index finger, should be going from north to south in that direction. And then what you want to do is to rotate your hand, but you don't really have to rotate it because it's actually already done, because the direction of the current is going away from you to whatever, maybe your door, your wall, whatever. So your hand is actually in the perfect position. And tell me where your thumb is. Your thumb is up in your father and mother roof, right? So D, A, or AD will be moving up, up, up. Now it says, name the rule used to determine the direction in which side dA of the coil moves. Hello, Fleming's left-hand rule. LMNOP, LMNOP. Remember, it's left-hand rule for motors, okay? Right-hand rule for generator. Don't forget it. All right. Explain why a split ring commutator is used in a DC motor. A split ring is fixed to the axles and it allows the coil to rotate. That's why it's there. It allows the coil to rotate by switching connection between the coil and the battery every half revolution as it rotates and rubs against the fixed graphite brushes or contacts. You realize the questions come back in a different way. You know, to just break them up. Okay, so now figure 7 shows a graph of the variation of voltage with time across the output terminals of an AC generator, right? And look what they did to you. They asked you to calculate the value of the frequency of the generator. They're playing smart, eh? So, this is what you need to remember. Frequency always refers to how many cycles are produced in 1 second, okay? So how many seconds we have here? They stopped at 0.05, as in they stopped labeling at 0.05 because that's what you're going to register. But really and truly, the graph ends at 0.06. These buggers. Horrible, you're already under stress. Why they do that? Now, how you measure wavelengths, just remember bump and trough. Or what I always do is go from one node of a full crest to the node of a full trough. That's one wavelength and that's one cycle. Then we have cycle number 2 and cycle number 3. So we have 3 cycles in 0.06 seconds. So therefore, X cycles will be produced in 1 second. And with a bit of cross multiplication to solve for X, we get 3 cycles times 1 second over 0.06 seconds, and we have 50 cycles per second. So 50 cycles will be produced in 1 second. That's the frequency, right? Now then they said the peak voltage is applied by the generator across 100 ohm resistor. Calculate the peak value of the current in the resistor. Just go back to the picture and look for the peak voltage, which would be this. Don't add 200 and 200. This is it's just 200, okay? So the peak voltage is 200, the resistance is 100, and then we're looking for current. And remember, voltage and resistance and current are all related when you use this equation. Voltage is equal to the current times the resistance, right? So current will be equal to voltage divided by resistance. You divide 200 volts by 100 ohms, you get 2 amps. The generator is subsequently rotated at twice the frequency. In B1, state the effect this will have on the period of the output, and the period will be halved. So what I did is say frequency is equal to 1 over T. So if you multiply or double the frequency and you want to solve for period, which is T, 2F will go underneath here, so it'll be half, as you can see here. And then it says here the value of the output voltage. Nothing will happen since voltage is not affected by frequency. Alright? Yeah. So I'm dropping some bombs, really and truly. I am dropping some bombs right now to you. Here. The transformer is a commonplace. So they like to bring this question to transformer questions. The transformer is a commonplace technological tool used in our daily lives. Figure 6 shows one type of transformer used in electricity distribution. State the name of the parts labeled A, B, C, and D in figure 6. Okay, so you need to know your parts. So this side, the left hand side, is always referred to as the primary coils. Even if you have a lot more coils on this side, the left hand side is the primary side and the right hand side is the secondary side. Okay, the amount of coils, however, tells us what type of transformer you have. So this type of transformer is a step up because you have more coils on the right than on the left. If you had more coils on the left and less coils on the right, it would be a step down, right? But just remember, your left hand side is called the primary side and the right hand side is called the secondary side. So in labeling it, we know that A is the primary coil, B is a soft iron core, C is alternating current or power source, and D is the secondary coils. Then it says identify the type of transformer shown in figure 6, and it's a step up because you have more coils on the right than on the left. And so state the formula that relates voltage to number of turns N in a transformer, and that will be NS in the secondary over NP, that's primary. And if you have the secondary over primary here, you relate it to the voltage in the secondary over voltage in the primary. That's how they relate it. Or you could have NP over NS equal to VP over VS. Yeah. So you can have it like that. Now, here we have a transformer has 5,000 turns in its secondary coil and 50 turns in its primary coil. The voltage supplied to its primary coil is 12 volts and a current of 6 amps flows in its primary coil. Calculate the output power of the transformer. Okay. So, sorry, calculate the input power of the transformer. So, as I said, when you have these questions, always write out your variables. You have your NS 5000, NP 50, VS question mark, VP 12 volts, IS question mark, IP 6 amps. Now, your current, if you have IS, which is secondary over primary, everything will be primary over secondary. Or you could have it like this: IP over IS equal to VS over VP, and then you would have NS over MP. You can change it around. All right, so this is the input power. So we're going to all look at the inputs. So power is related to current and voltage. It's a product of current and voltage. PIV. And so the power here will be I in the primary section times the voltage in the primary section, and we have it here. We have the I and the V. So we have them. So I have 12 times 6 will give us 72 watts. Now then they said they wanted to solve the voltage across the secondary coil. So we have NS over MP equal to VS over VP. And since we're looking for VS, we could solve for VS one time, make it the subject of the formula, where we have NS times VP over NP. And then we just substitute. Given we have it laid out up here, we just put them in. We have VS is equal to 5,000 times 12 volts over 50, and that gives us 1200 volts to max. Then the maximum secondary current, if the transformer is 100% efficient, meaning that and that would never happen, but just let's ignore heat loss and any other energy transformations, right? And to find the secondary current, we could have here NS over NP equal to IP over IS. We can have it like that. Just remember, with current, it's different, it flips, right? So what I would do now is solve for IS, because it asks for the current in the secondary side. So IS will be equal to NP over NP IP over NS. So you just transpose, like this goes up, this comes down, this goes up, right? So IS will be equal to 50 times 6 amps over 5,000, and you see that you have a current of 0.06 amps. Okay, so here's another transformer question. I think this was 2021, I'm not sure. But we just labeled the pattern. This is another way they would have it. And we already know that X will be the alternating current or the power source. Y is the secondary, because this is the right hand side. And Z is the soft iron core. And then now, so this was a part of a question that was probably a graph, and I left graphs out for a while. And so I just took this part of the question. All right, so 5. A semiconductor diode is used in a half-wave rectification. Using the axes in figure 6, sketch the IV graph for the semiconducting diode, and this is how it looks. This is exactly how it looks, right? It's not an ohmic conductor. Remember, ohmic conductors will produce graphs with a straight line graph and IV right here, right? Okay, and here we have a truth table with this question with a NAND gate. So a NAND gate is an AND gate that is connected to a NOT gate, right? So a NAND gate, remember the AND gate looks like this? And an AND gate looks like this, and we say the AND gate is a multiplier. So with an AND gate, you would have had the same inputs. So you would have an input of 0, 0, 0, 1, 1, 0, and 1, 1. and because it's a multiplier, your output would have been 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1, right? But seeing as how we're dealing with a NAND gate, your NAND gate is actually attached to a NOT gate. And the condense is drawing by doing the NAND gate like this. Okay? The condense is drawing. And so, because you have the NOT gate here, it will convert all of these to ones. 0 to 1 and 1 to 0. So, if you have a 0, it will be converted to 1. Another 0, 1. Another 0, 1. And then 1 will be converted to 0 because we have the converter attached. Right? That's all that's happening. Okay? Okay, figure 7 shows 3 resistors in series of values 2 ohms, 5 ohms, and 10 ohms. So it says calculate the equivalent resistance of the resistors shown in figure 7. And seeing as how it's in series, all you have to do is add them up. Just add them like regular. So 2 plus 5 plus 10 gives us 17. Now the when I put the same resistors in parallel, right? In parallel is a little different. You would say 1, and this is C, so no, it's not 2, it's 3. And in this case, 3 is like a stepwise, so you have to use the 1 over RP. So when you use 1 over RP equal to 1 over each of these resistors here, you have to find a common denominator, and we found that it was 10. Whatever you do to the bottom, you have to do to the top, okay? We end up with 5 plus 2 plus 1 is equal to 8 over 10. Now, once you get the 8 over 10, you can't forget to transpose to get RP out to being in the reciprocal. So you have to flip it. And so what you would do is transpose 10 up here, bring 8 down here, and carry RP up. So you will end up with RP is equal to 10 over 8. And so overall, 10 over 8 is equal to 1.25 ohms. Now the resistors in figure 7 were connected, so it's figure 7, oh, over there. So the resistors in figure 8, were connected in a circuit to a 6-volt power supply. So this is where you have to remember how voltage, current, and resistance are related. They're related by saying a voltage is equal to current times resistance, right? They ask you for the current, we are given the voltage, we solve for the resistance up here, right? The total resistance is 1.25, and so we divide 6 volts by 1.25, the current is 4.8 amps. Alright everybody, good luck on the electricity section. I hope you get questions like these, and I hope you're able to play over my video at least 100 times tonight. I know it's late, but I have so many responsibilities. Anyway, you don't need to hear about all of that. Good luck, my students. Look out for my next video. It's probably gonna be on waves, sound, and light, using questions, past paper questions from different past papers. Duh. And some explanations in between. I hope this helped. Write something down if it didn't help. Write something down if it helped. Ask your questions, and don't forget to holler. Okay, bye. See you.